In this video, we're going to look at how to calculate the freezing point depression for a solution. So as we know, at the freezing temperature, the solid and liquid phases are in equilibrium. And we also know that the freezing temperature of a solution is going to be lower than the freezing temperature of an equal volume of pure solvent. So if you have a pure solvent, you add a solute to it, the freezing point will be depressed. How can we calculate the change in the freezing point for a solution compared to that of the pure solvent? Well, we can use this formula. And in this formula, the delta TF is the change in the freezing point, and that's the freezing point of the pure solvent minus the freezing point of the solution. Kf is a Malau freezing point depression constant. So it's a constant that depends on the solvent that's being used. Each solvent has its own unique Kf value. M is the molality of the solute in our solution. And I is something called the Van't Hoff factor. So we're familiar with molality, freezing point, and our Kf, but let's talk about the Van't Hoff factor for a minute. Colligative properties like freezing point depression depend on the amount of dissolved particles in solution. So when we put an electrolyte, maybe an ionic compound or something in solution, it's going to dissociate to give us more particles in solution or more ions. So we have to take into account the dissociation of our electrolytes in solution. So the Van't Hoff factor is basically a measure of how much dissociation we have. It's equal to the moles of particles that are in solution, this may be ions in solution, over the moles of solute that were dissolved. So let's look at an example. The Van't Hoff factor for non-electrolytes is 1 because for every mole of solute that you put in, you get 1 mole of particles. In other words, it does not dissociate. So the moles of particles and the moles of solute that you started with are the same. The Van't Hoff factor for ionic compounds, however, is not 1, and it depends on the moles of ions that are formed and the degree of dissociation. So let's look at an example to illustrate this. If you put 1 mole of sodium chloride in solution, it would dissociate to give you 1 mole of sodium and 1 mole of chloride ions. So for every 1 mole of sodium chloride that we started with, we would expect to get 2 moles of particles. So our Van't Hoff factor we would expect to be 2. And for sodium chloride, the Van't Hoff factor is actually very close to 2. It's 1.9. And it's not exactly 2 because you don't get a complete 100% dissociation for sodium chloride, but as you can see, it's very close to 2. If we looked at another ionic compound, magnesium chloride, for every 1 mole of magnesium chloride that we dissolved, we would get 1 mole of magnesium and 2 moles of chloride ions. So for every 1 mole of magnesium chloride that we started with, we would get 3 moles of particles or 3 moles of ions. At least we would predict that. So our Van't Hoff factor for something like magnesium chloride, we would predict to be 3. And the Van't Hoff factor for magnesium chloride, again, predicted is 3. Experimentally, it's 2.7. So it's generally going to be a little less than predicted because you don't always have 100% dissociation. So take a look at this problem, pause the video, and see if you can calculate the freezing point for this solution. Okay, so let's take a look at this. We want to calculate the freezing point for this solution, for this magnesium chloride solution, based on the information that's given. First thing I would do is let's calculate the moles of magnesium chloride. We need this in order to calculate our molality. Now that we have our moles, we take our grams divided by the molar mass to give us the moles of magnesium chloride. We can divide the moles of our solute, magnesium chloride, by the kilograms. We're given grams, but we want to convert that to kilograms of our solvent in order to get the molality. So we take the moles and divide that by our kilograms, and we get a molality of 0.17 moles per kilogram. Now that we have our molality, we're given the Kf value. We have calculated our molality, and we were also given the Van't Hoff factor for magnesium chloride. So we just multiply all of those together. We take our Kf value times our molality times our Van't Hoff factor, which has no units. And we can see that our units of moles cancel, our units of kilograms cancel, and we end up with a delta TF, so the change in freezing point is 3.6. Now, water is our solvent, and we know that water has a freezing temperature of 0 degrees Celsius. The change in freezing point is 3.6. So the 3.6 is not the new freezing point, that's the change in freezing point. In order to calculate the final freezing point, or the actual freezing point of our solution, we would subtract the change in freezing point from our actual freezing point, and we would get negative 3.6. So as you can see, our freezing point is depressed or lowered by 3.6 degrees, and in water that would correspond to a final freezing temperature of negative 3.6 degrees Celsius. So be sure you practice a few more of these freezing point problems, and be sure you can calculate any of these constants or any of this information that's asked.